Hi everyone, good evening. Am I audible? Can somebody please confirm?
Yes, ma'am, audible.
Thank you. My screen is visible.
Yes, ma'am.
We'll start in another couple of minutes. Yeah, good evening everyone. Welcome to week 7 live interactive session on introduction to operating system. So today the topic that will be discussed is basically on deadlocks and little on threads. Okay, so we'll get started.
Your voice is not coming. You are muted.
Yeah, yeah, give me a minute. Yeah. Yeah, yeah. So let's get started. So the topic that we have today is on deadlock, and deadlock is a scenario that comes into picture when we talk about resource allocations. Okay. So let's one of the famous examples that we used to discuss deadlock is the dining philosopher's problem. And I'm audible now, right?
Yes, ma'am.
No. So this is one of the most commonly used example to get started with the concept of deadlock. So what does this dining philosophers is that we assume this there is a dining table over which some five philosophers are sitting over here. One, two, three, four, and five. Of that, their job is to think for some time, and then when they feel hungry, they will start eating. So for all the five of them, we will have five plates to eat the food, and all of them will have a fork also. Okay, there are five forks available. Okay, so there are five people, five plates, and five forks available, and for each philosopher to eat it needs two fork. So to eat they need two fork. So for example, if this is p1, p2, p3, p4, and p5, if philosopher p1 wants to eat, it will take hold of the left and right fork, it will start eating. So when p1 is eating, p5 will not be able to eat because one fork is it's already been used, right? So p5 will not be able to eat. Same way p2 also will not be able to eat because this particular fork is being used by P1. But whereas P4 and P3 can actually eat when P1 is eating. So this is the concept of dining philosopher problem, and the problem that we are trying to look at here is we have to develop a solution such that none of the philosophers will be starving. Mm. So the problem here is that uh, design an algorithm such that
And your screen is not visible.
screen is not visible. Okay,
Yes, ma'am.
right. Mm. Such that no philosopher is hungry or starving. So if we just think that okay, all of them are like thinking, and suddenly all the five of them take the left fork in their hand or maybe right fork in their hand, then how will the situation be? So for example, P1, P2, P3, P4, and P5, all of them were thinking, and suddenly at the same time they felt hunger, and they started taking the right fork. So P1 will take this fork. P2 will take this. It will be with P2. This fork will be with P3. This fork will be with P4, and this one will be with P5. Okay, so P1 will have one fork with it, P2 will have one fork with it, P3 will have one, P4 will have, and P5. All of them will be holding one and waiting for the other to release the second one. So, what kind of a situation is this? Will they be releasing? Like P1 have this fork with it and it's waiting for P2 to release. Same way, P2 is having one fork with it and P2 is waiting for P3 to release this one. Same way, P3 is having this fork and P3 is expecting P4 to release this. And P4 is having this fork and P4 is expecting P5 to release. Same way, P5 is having this and P5 is expecting P1 to release. So all the five of them are in which state now? So all five of them are currently in a block state, right? Though all of them have one fork with them, none of them is able to proceed with eating because they are not getting the second fork. Okay, so the situation of nobody proceeding, all of them are stuck at a point, and P1 can proceed only if P2 release, but P2 is also waiting for P3 to release, but P3 is also waiting, P4 is also, so it's in a loop. All of them are waiting for the resource present in the other one's hand. So the situation is actually called a deadlock situation. Okay. So the situation is called a deadlock situation. That is when the programs continue to run indefinitely without making any progress. They, all the five of them is continue to wait without making any progress. So here the progress is like they are hungry, they should be eating, but none of them is not even able to start the eating process. So deadlock is, so this situation is called a deadlock situation. That is programs continue to run indefinitely without making any without making any progress. So this is the this is what we call as deadlock. So this happens when the resources are not available for the processes to proceed. So if the resources are not allocated properly, there is a chance of deadlock to occur. And if deadlock occur, then the system will come to a standstill kind of a situation. Sometimes we observe, right, in the traffic signals and all, if so, for example, I mean, in recently we I have observed near to my home there was a circle like this. Okay, they have built a circle here. So people, there is a road this way. There is a road this way, like this also, and they could go like this. People could go like this, and it used to actually jam. So in the evenings during the peak traffic time, there will be a lot of people to go like this, many to come like this. Same way, there used to be a lot to go this way and this way. So finally, if some jam happens here, this whole circle used to become a deadlock situation. Okay. So similarly, in many of the traffic junctions, if we have this kind of a traffic junctions, we do see like sometimes if the signals are not working, we don't follow the rules properly. All the cars, bikes, everybody will come, and it will lead to a jam wherein no one will be in a position to move and proceed further. So that is it's equivalent of a deadlock situation where none of the vehicles are moving to their destination. Same way, when resources are not available and each process is waiting for some resource which is with another process, the situation of deadlock will occur. Now, how can we solve this dining philosophers problem? That is, how can we ensure that these philosophers do get a chance to eat? So we can use mechanisms like semaphore mechanism, mutex and semaphore, and make sure that when P2 P2 like you can we can log the, because these are shared resources, right? These forks are shared resource between the philosophers, so we can bring in some kind of a locking mechanism, that, and also making sure that before, if P2 is taking the right fork, make sure that the left is available only, then the right is taken. So using mutex and semaphores, we can solve this. That you can go through the lecture video, like how, what are the possible solutions of dining philosophers problem. Okay. Now, with respect to deadlock, yeah. So hope you understood this concept of deadlock, right?
Yes, ma'am.
Yeah. So now coming back to the computer science terms, here the philosophers, if we take philosophers, are equivalent to the processes, and fork is equivalent of resources, system resources. Okay, so normally we use something when we talk about deadlock, the like the resources processes. We have something called as a resource allocation graph. We will first see what a resource allocation graph is, and then we will see how we can utilize this resource allocation graph to figure out if there is a deadlock or not. By the way, the deadlock situation is not good for the system, because the system or the processes do not make any progress. So ideally, we don't want our system to get into a deadlock situation. Now, if a deadlock occur, then we would want to detect it or prevent it or avoid it. So we'll see to all that. So before we see all that, let's see what this resource allocation graph is. So let's assume that we have a process in the resource allocation graph. It is nothing but it's a way of representing the resources allocated to each process. So processes are represented as ovals, P1, P2, like this in oval shape. Though I am not drawing it as oval, it's actually should be an oval. Then resources are represented as square boxes, is R1, R2, like that, Rn. Now, if we have a situation where process hmm, or okay resource. R1 is allocated to P1, then if R1 is allocated to P1, then we will have an arrow from R1 to P1. So this is how we represent that R1 is now with process P1. Okay. Now if the situation is R2, sorry, P2 request R. Okay, sorry, request R1. Now here we know R1 is allocated to P1, and now if P2 makes a request, then the arrow will be from P2 to R1, because P2 have requested for R1, but it is not given yet. Okay. So this is the terminology, or this is how we draw the graph. So if the process holds a resource, so it will be process. So P1 holds R1. So the arrow is towards P1, which means R1 is with P1. Okay. Now, same way, if P2 is given R2, it will be like this. P2 holds R2. Now, if P3 have requested R3, so it is P3 requested R3. So this is how, based on the allocation information, we come up with a resource allocation graph. Okay. Now, using a resource allocation graph, how we can represent a deadlock situation is, suppose we have process P1, we have P1, we have P2, and we have R1 and we have R2. Now, we have a situation where P1 is allocated R1, R1 is given to P1, and P2 is R2 is allocated to P2. Okay. Now, at the same time, P1 is holding R1. At the same time, P1 has also requested for R2. Requested for R2. And also, P2, while holding R2, have requested R1. So now if you see here, P1 requires R1 and R2. Same way P2 requires R1 and R2. P1 has R1 but is waiting for R2. That is this one, this arrow, and this arrow. So P1 holds R1 and P1 is waiting for R2. Same way P2 holds R2. P2 have R2 with it. But P2 also needs R1. But R1 is with P1. But P1 is waiting for R2. And R2 is with P2. P2 will not release R2 until it gets R1. So this is a deadlock situation. And if you see here, when in a resource allocation graph, you can see that there is a cycle formed here. So can you see a cycle? 1, 2, 3, 4. So it's a cycle, right? Directed graph may, if you see, if you traverse the edges, we get a cycle here. So R1, R1, P1, then P1, R2, sorry, P1, R2. That is, these are the edges, the order in which we traverse. Then R2, P2, and P2, R1. So this forms a cycle here. So if the resource allocation graph has a cycle, then we can say that there is a deadlock. So this applies only if the number of instances of the resource is one. That is, there is only one instance of R1. So if you see that R1 is a printer, one instance means that only one printer is there. So this is how we can represent the resource allocation, and we can identify if some deadlocks are there. So, in general, we have some necessary and sufficient conditions for a deadlock to occur in a system. We call them as necessary and sufficient condition for deadlock to occur. So it means there are four such conditions. These necessary and sufficient conditions mean that if any of these conditions is broken, then it means that deadlock will not occur. Okay. One minute. Huh. So the first condition for condition is mutual exclusion. So these are the conditions necessary for a deadlock to occur. Okay. So if we can break any of these conditions, then we can ensure that a deadlock will not occur in the system. So if all these conditions are met, it implies that there is a potential uh, there is a potential chance for deadlock to occur. Okay. One is mutual exclusion. Mutual exclusions means that each resource can be with only one particular process. Like critical section, we saw, right? Only one process should be in the critical section at a given point of time. Similar to that, mutual exclusion means that each resource is either available or assigned to exactly one process. Each resource is, that is, the resource cannot be shared. Resources. So, what I mean by resources cannot be shared, it cannot be simultaneously shared. So, hold and wait. Hold and wait means that if a process is holding a resource and it is requesting another resource, like in this scenario, P1 is holding R1, P1 is holding R1 and it is requesting R2. So this is a hold and wait scenario. Okay. So you are holding a resource and then you are requesting another resource. Yeah. Then third one is no preemption. No preemption means that when a particular resource is granted to a particular process, the OS cannot forcibly take back the resource from it. The process have to voluntarily release the resource once the utilization is done. So that is what no preemption means. That is resources granted can't be forcibly taken away. Fourth one is circular weight. Circular weight means that there must be a circular chain of two or more processes. So, like we saw in the dining philosopher's problem, right? So, we have philosopher 1, 2, 3, 4, and 5. And assume that so we have fork 1, P2, yeah, F1. F2, F3, F4, and F5. So, sorry, I should write this towards this side. Yeah. F1, F1, F2, F3, F4, and F5. Okay, so we have seen that here P1 is waiting for F2, P2 is waiting for F3, P3 is waiting for F4, P4 is waiting for F5, and P5 is waiting for F1. So this kind of a equation is called a circular wait. So there must be a circular chain of two or more processes. Each of them is waiting for the resource held by the other. So P1 contains F1. So F1 is here. So each of them, P1 is waiting for a resource that is with P2. P2 is waiting for a resource that's with P3. P3 is waiting for a resource that's with P4, and P4 is waiting for a resource that is with P5. In turn, P5 is waiting for a resource that is with P1. So this is called a circular wait. So if all four of these conditions are present, or we can say that all four conditions must be present present for a deadlock to occur. I mean, resource deadlock to occur in the system. So, if any of this condition is not satisfied, then we can say that deadlock will not occur. Okay. So, now let's see a simple example that is discussed in the class and see the resource allocation and how a particular change in the resource requirement leads to the deadlock state. So we have A, process B, and process C is there. Process A will request R, then it requests S, then it requests R and S. Same way, S, T, S, and T, and C is requesting T, R, T, and R. Hmm. So these are the, but the order in which they are requesting is A will request for R, then B is asking for S, then C is asking for T, then A is asked for S, then B for T, and C is asking for R. So initially, so we have A, we have B, and we have C. We have R, S, and T are the resources. Correct? R, S, and T. So first, A is asking for R. So R is free. So R is allocated to A. Now after that, B is asking for S. S is currently free. So B is given S. Now C is asking for T. It is given. Now after that, A is requesting for S. So request we can give. A is requesting S. So which side the arrow will be?
Ma'am, towards S.
Yeah, so here, yeah. Then this is done. Now B have requested for T and C have requested for R. So what condition is this? What situation is this?
Deadlock.
So this is a deadlock situation. So if you see the we have a cycle here, right? Okay, sorry. Hmm. So we can see a cycle here, right? Like this, like this, like this, like this, and then back to the place where we start. Okay, so there is a cycle here. Now, so there is a so what happens here? Deadlock occur. So, if this particular set of resources are requested in this order, then a deadlock occur. So in deadlock scenario, the order in which the processes request the resource matter. So now if we change the order slightly, like for example, if we assume that A is requesting R first, then C is requesting T, then A is requesting S, then C is requesting R, then A is requesting R, and then request. A releases R. So A is um, releasing R, releasing S. Then again A is releasing S. So now let's see how the resource allocation graph will be. So we will have A, B, and C. We have R, S, and T. So initially A is requesting for R. So how will the direction be? A to R or R to A?
A to R.
A is requesting for R. Okay, so R is free, right? R is available. So it will be given. Okay. Then C is asking for T. T is free. So T will be allotted to C. Now A is asking for S. S is also currently free. So S is also given to A. Now the next one is C is asking for R. C is asking for R, but R is already allotted. So it will be a request. Okay. So now A is releasing R. So releasing R is this is done. Okay. Now when A releases R, this arrow will change and then it will be R will be allotted to C. Once the resource become free, it will be allocated to C. So it will be given to C. Now after that A is releasing S also. So this is also done. So now do we have any cycle? There is no cycle also. Whatever C have asked, C have got also. So this set of what to say? This sequence of request and release does not lead to a deadlock. Correct? This does not lead to a so deadlock depends on the order in which each process requests the resources. Okay. So hope this is clear. Now the question here is deadlock important? Do we need to handle it? If we can handle, what are the ways to handle it? So deadlock is important because if the system gets into a deadlock scenario, then nothing will move, right? Have you ever observed like your laptop hanging off laptop, like you have some 10, 15 browsers opened and you have not rebooted or shut down your laptop for a couple of days or weeks? Did you ever observe that slowly the laptop becomes slow and then it stops responding, and then you had to do a reboot or forceful restart of the laptop? Yeah, that's something to do with this situation only. Okay. So in most of the time, deadlock is not. There are like if a deadlock occur, either the operating system can detect and recover from the deadlock, either it can have strategy to prevent it, or we can have avoidance mechanism. That is how we can handle deadlock is either you detect and recover. Another way is to avoid completely. Another way is to prevent it from happening. Another way is to ignore it. Most of the Ubuntu Linux-based operating system ignore it because we run it on the desktop machines, right? So there isn't much of a critical applications and all that will be running. So they ignore, and so when it hangs, we have to do the reboot and all that. But there are other systems where deadlock is very critical, like real-time operating systems and all. This cannot happen. So there, the deadlock will be handled. Okay. So, so the mechanism is detection and recovery, avoidance and prevention. So how can we detect the deadlock? One way is to, how do we detect whether the system is in a deadlock situation or not? So one way to detect deadlock is, for example, if we have only single instances of the resources, we can easily draw the resource allocation graph. We can have the resource allocation graph and then we can check for the cycles. But majority of the times resources, there will be multiple instances of the resources. So checking for a cycle will not help. So a cycle doesn't always say that there is a deadlock when the number of instances are more than one. So then what we have to do is we need to see the current allocation. The operating system, if it wants to detect it, it has to see the current what is the allocation, how many resources are allocated to each process, how many requests are made by each process, and what is the maximum number of available resources, and what are the needs. All these information need to be checked, and then we need to see there is a if there are any deadlock situation present or not. Okay, so we call these current allocation, the request, current request and all are in a metric format. Okay, so we call them as allocation metrics, request metrics, etc. So how we draw the allocation matrix is, for example, we have three processes, P1, P2 and P3. Sorry, let me do it the other way. So we have three processes, P1, P2 and P3, and we have maybe four resources, R1, R2, R3 and R4. Now, the allocation metric will tell that how much of R1 is allotted to P1, how many R2 is allotted to P1. This row will tell R1's allocation. This row will tell R2, sorry, the other way. This row will tell P1's allocation. This will tell P2's allocation. This will tell P3, how many resources are given. So if you see in a column-wise manner, it will tell R1's allocation. R1, how many R1 is given to P1, how many R1 is given to P2, how many R1 is given to P3. For example, if the number is 0, 2 and 0, it means that 0 instance of R1 is allotted to P1. Two instances of R1 is given to P2. That is, P2 is holding two instances of R1 and 0 instances of R1 is given to P3. That is, P3 doesn't have R1. Okay. So same way, R2, if we see 0, 0, 1, 1, 0, 2 and 0, 1, 0. So if you see here, if you see it in a row wise, we can see that P1, how many resources does P1 hold? Can somebody tell?
Only resource 3.
Yeah, so if you look in the row wise manner, you can see that, okay, P1 have 0 R1, 0 R2, 1 R3 and 0 R4. Same way P2 have, look in the row wise manner, P2 have 2 R1, 0 R2, 0 R3 and 1 R4. P3 have 0 R1, 1 R2, 2 R3 and 0 R4. Okay. So this is the allocation metric. This is currently what each process is given. Okay. So there is something called allocation, then requests, then we have existing resources, then we have free available resources. So we'll cross check all these matrices and then find out whether if there is any sequence of allocation by which all the current requests can be met. If such a sequence of allocation is available, when then we say that there is no deadlock situation. Maybe we can see one example. Probably that would make it little easy to understand. For example, assume that the maximum request, okay, maximum requests from all the process. We have three process, P0, P1 and P2. We have three requests, sorry, resources R1, R2 and R3. Okay, so P0 needs a maximum of 8. Okay. So, what does it mean? P0 needs a maximum of 8 R1, 4 R2 and 3 R3. Same way, P1 needs a maximum of 6 R1, 2 R2 and 0 R3. So, during its lifetime, this process will be, this is the maximum number this process will be asking for. That is the max number of requests this process will make. Now, there is another information, that is the allocation. Currently, how much is allocated to each of them? P0, P1 and P2, R1, R2 and R3. So the allocation is 0, 0, 1 for P1, 3, 2, 0 for P2 and 2, 1, 1 for P2. Okay. Now, can you tell me what will be the need matrix? Need matrix means how many more would each process require? P0, P1, P2, R1, R2, R3. So, what I mean by need is P0 requires during its whole execution lifetime, P0 requires 8, so 8 instances of R1. Okay. Currently, it is allocated 0 instances. So, how many more does P0 need? 8. So, that is what need represent. Okay. So, how many more, how many R2 does P0 need?
4.
Needs 4 more. And R3?
2.
P1? It requires 6. It is already given 3. How many more does it need? 3 more, right? Then it requires 0 and allotted 0. Now P2? P2?
1.
It 1, 1, 2 and 2. Okay. Now we need one more thing. What are the currently some what free resources. Number of free resources R1, R2, R3. How many more are available? It is called available, not free, sorry. Available resources. So this available is after this allocation, okay? So after the allocation, how many more are available? That is given as 3, 2. Okay, so given this information, can sorry. Doubt. Chalo. Okay, so now from this information, we need to find out if there is a possible scenario wherein we can schedule these requests such that all the three processes can go to completion. If there is there a way we can meet this need? In which sequence do we need to process them? Like, should P not be given first, P followed by P1, followed by P2, or P1, P2, P naught, or in which order, if we service these requests, can all the three of them complete their execution? Is such an order is possible? Then, okay, the system is not in deadlock. If such a sequence is not possible, then we say the system is in deadlock. Can we find if such a sequence is possible? So currently, so let's start from P naught. Currently we have 3, we have 2 and we have 2. P naught require 8, 4 and 2. Will we be able to schedule P naught now? Will P naught be able to complete?
No, ma'am.
No. Can we schedule P1?
Yes, ma'am.
P1 needs 3 more, then 0, 0. Okay, now let's assume that we have scheduled P1. Okay, so P1 is scheduled. So this 3 is given to P1. So the available will become 0. Now once P1 completes its execution, so the available resources, so whatever is there with P1, that will be released, right? Yes or no?
Yes, ma'am.
So what are the resources available with P1? We have given 3 and another 3. So 6 will come here. After P1 is executed, 6 instances of R1 will be released. Then R2, 2 instance will be released. So already 2 is available. To it, 2 more will be added. So totally 4 will now become available. And P1 did not want any R3. Neither was it allotted nor it required. So it will remain the same. Now we have 6, 4, 2 available with us and P1 is done. Now which process shall we schedule?
Ma'am, how resource 2 becomes 4?
R2, because P1 already had 2. P1 was given 2. P1 was holding 2. So when P1 completes its execution, right, this 2 will also come to this list of available resources. So already 2 available tha, uske साथ another 2 more becomes available. So it becomes 4.
Okay, ma'am.
So when a process completes, right, all whatever it is allocated, all that will be released. Okay. So now we have 6 R1, 4 R2 and 2 R3. Now which process can we schedule? Can we go for P naught? P naught needs 8, but only 6 is available. So we can, P naught cannot complete its execution. So now the next process is P2. P2 needs 1 R1, we have 6. P2 needs 2 more R2, we have 4, and 2 more R3, we have 2. So we can, let's see if, let's give the resources to P1 now. So, now from the 6, we gave 1 to P1, so it becomes 5. 2 to P2, and then again another 2 to P2. So now P1, P2 is executing. Okay, so we gave 1, we gave 2, and we gave 2. So because of that, I reduced it accordingly. Now currently available is 5, 2, and 0, and P2 is currently executing. Okay, now after some time, P2 will complete its execution, and once it completes its execution, whatever was there with P2 all will be released. So P2 had 2 R1 and 1 R1. So 2 plus 1, 3 R1 was there. So plus 3. So how much it will be? 5 plus 3, 8. P2 also already had 1, then we gave 2. So total P2 had 3 R2. So 3 plus, already we had 2, and uske saath we add another 3, which is 5. Now R3, P2 had 2 and also 1. So 2 plus 1, 3. So now we are left with 8, 5 and 3. Now can we schedule P0?
Yes,
P0
ma'am.
require 8, 4 and 2. We have 8, 5 and 3. So now easily P0 can execute. So this is the sequence. So there is a sequence, right? So there is no. So we are able to find a sequence. So there is no deadlock in the system. Okay, that is how this deadlock detection mechanism would work. Okay. Now the next one is deadlock. Once we detect the deadlock, how can we recover it? So one simple way to recover is to recovery mechanism. One simple recovery way to do the recovery is to raise an alarm. Then another way is to perform preemption. So if we observe that there have been a deadlock situation, and the system will not be, we are not able to find a sequence of execution, then what we can do is we can temporarily release some resource from already given process, and then start the execution. So that is what preemption means. So this is also one of the criteria, right? No preemption is a criteria for deadlock. So if we bring in preemption, then we can stop the solve the deadlock situation. Another one is to do a rollback. So rollback is nothing but to keep some checkpoint mechanism and then come back to that places. So as the process executes, as P1, P2, P3, as they execute, at certain points during the execution, certain checkpoints are taken and saved in the drive. And if a deadlock sits, for example, somewhere here during the execution, if we observe that a deadlock occur, we will roll back to this checkpoint, and then we will continue from there. Okay. And another way is to kill one of the low priority process. So with this, all the resources that this low priority process is holding will come to the system, and then one another process might be able to proceed, and thus we will be able to come out of the deadlock situation. That is about deadlock detection and recovery. Another mechanism is deadlock avoidance. So in the Deadlock avoidance scenario, what we do is we proactively observe the current state and see whether the execution sequences might take the system to a unsafe state or not. An unsafe state does not mean that it is a deadlock, but unsafe state means that there's a potential scenario, the probability of deadlock to occur is higher. So that is about deadlock avoidance. So we categorize something called we'll check whether the system state is a safe state or an unsafe state, and then accordingly we will proceed. So for every request, this system state is looked upon, and if a particular resource request takes the system to an unsafe state, then we try to avoid it. So that is about deadlock avoidance, and then deadlock prevention is another thing. Here we talked about safe state and unsafe. Deadlock prevention is basically making sure that we had the prevent like we have the four necessary condition for deadlock. So if we make sure that one of this scenario does not happen, then we can make sure we can prevent deadlock. So if we sometimes mutual exclusion is something which cannot be broken. So mutual exclusion needs to happen. Hold and wait is something we can work on. That is, if a process is already holding a couple of resource and it is requesting, we can ensure that that is not allowed. So either the process have to request and keep all its needed resources at the very first, or if it is requesting for additional resource, and then it has to release all that and make the whole request once again. So such a mechanism can be thought about, though of course not an optimal way, but hold and wait is something which can be achieved, like which can be broken. So if we prevent any of these scenario, then deadlock will not occur. So hold and wait is something that can be handled in that way. No preemption says that if somebody is holding a resource, while the system cannot force that process to release the resource. So if that is possible, again we can prevent it. Like if preemption of resources is possible, then we can prevent deadlock. Similar way, circular weight also. So circular weight, we have seen, right, in an ordered manner, people are requesting. So if we make sure that that cycle should not happen from the, like from philosopher 5, it was requesting fork 1. So if we ensure that there is an ordering in the request, or request can always be made in an hierarchical manner, then that request from P5 to F1 will not happen, and thus one can prevent deadlock. So that is about deadlock. Maybe we can see a few examples more. Yeah. One more example. So we have P1. P2, P3, P4. The max allocation is 8, 2, 3, 4, 8, 5, 9, 7, 1, and 7, 0, 4. Currently, allocated is 3, 1, 0, 3, 8, 4, 9, 6, 0, and 0, 0, 4. Need is how many more each of them require. So what is the need here? Can you tell me the need?
Ma'am, 5, 1, 3,
Hmm.
1, 0, 1,
Hmm.
0, double 1,
Hmm.
7, 0, 0.
Hmm. Now available is 2, 1, and 2. So, what is a potential sequence that can take the processes to completion? So, which of the two processes can be given the resources now? P1 needs 5, 1, and 3. We don't have 5, right? For R1, we don't have 5. And for R3 also, we don't have 3. We have only 2, 1, and 2. So, P1 cannot be given now. Same way, P4 cannot be given now. P4 needs 7, and we have only 2 with us currently. So, which one we can go for?
P2.
P2 or P3, correct?
Yes, ma'am.
Now, if you go for P2, P2 needs 1, 0, and 1. Okay, so we have that. Now, once P2 is executed, how many will come to the list of free this one? So, if P2 completes execution, uh, it becomes 5, this one 9, and 4 plus 2, 6, correct?
Ma'am, how we calculate that after the process complete, how many resources are available?
Yeah, you tell me how many resources will be available once P2 is completed.
Ma'am, I think the allocation resources will be given back to the available.
Hmm. Yes, so ideally how it happens is from the available 1, 0, 1 will go here. Okay, so 1, 0, 1 from the available will go. So available will become 1, 1, and 1. Correct?
Yes, ma'am.
Okay, so now we have 1, 1, and 1. Okay, so now P2 is having 384 and 101. That is 485. P2 is having all 485 with it. Yes.
Yes, ma'am.
So now once P2 is completed, 4, 8, and 5 will come to the available list. That is 4, 8, and 5. So 5 plus 1, 6, 8 plus 1, 9, 4 plus 1, 5.
Okay, ma'am.
So this is one way of doing it, but this is equivalent is this is equal to. So now we know that We know that from the available, we will give the need and then P2 will run to completion. So whatever is there in the alloc, you don't need to always subtract this, write the updated avail, then sum up this two and so what I actually did is I did a minus 101, then I did a plus 384 plus 101. This is not actually needed. You can directly add the alloc to the avail. Okay.
Yes, ma'am.
Once you understand, you can do it that way, but until you fully understand, you can go with the step by step approach. Is this clear with everyone? So, 5, 9, 6. Okay, so we have 5, 9, and 6 now. Now, okay, now which process can we schedule? We can schedule any of them,
When
right?
it
We
we
can,
both can
yeah,
execute.
we can go for P1, we can go for P3, and we can even go for, we can't go for P5, P4, right? We can go for P1 and P3, correct? Yes or no?
Yes, ma'am.
Right. So let's give P1. So, so after that, after we give P1, this will become 8, 10, and 6. Correct?
Yes, ma'am.
And after that, now if we give P3, becomes 17, 16, and 6. Right?
Yes,
And
ma'am.
after that, if we give P4, then it becomes 17,
16, 10.
10. Right?
Yes, ma'am.
Okay. There is one more question similar to this in the previous year question paper. We'll discuss that now itself. The system has 5 processes and 3 resources. The max count of which is 10, 5, 7. Okay, can you tell the need?
Yes, ma'am. 7, 4, 3,
Hmm.
1, 2, 2, 6, 0, 0, 1, 1,
Hmm.
4, 3, 1.
How much is the available? This is the total available. That is maximum number of resource R1, maximum number of resource R2 and R3. Okay, 10, 5 and 7. From this, it is allocated. Now let's sum up how many are allocated and find out what are the available free. Okay, so for 2 plus 2, 4 plus 1, 5, 2, 7, right? 7 to 5 is already allocated. So how many are available now?
3, 3, 2.
Right. Okay. So now we have 3, 3, 2. Correct. So of this, uh, which one can we allot now? We can go for P1 or can P1 be executed? P not be executed?
No, ma'am.
P1? P1 can
Ma'am,
be
P2
executed?
and P1 and P3 can be executed.
Okay, let's go for P1. Okay. So if we allot to P1, then this will come here. So it becomes 5, 3, and 2. Okay. Available will increase by 5 will increase by 200 because this 122 is anyway being given from the available and then we are again going to add it. So let's not do that step. So whatever is here will come here. So 3 plus 2 5, 3 plus 0 3 and 2 plus 0 2. Now we have 5 3 2. Now which one can we allocate? 5 3 2. Which are the processes that we can P not execute with this available resources? P naught requires 7, 4, and 3, but we have only 5, so P naught cannot execute. P2 requires 6, 0, 0, but we have only 5 here, so P2 also cannot. P3 needs 0, 1, 1, which can, and P4 needs 4, 3, 1, so that also can execute. Let's take P3. So P3, if P3 runs to completion, then this 211 will also come to the available set. So 5 plus 2, 7, 3 plus 1, 4, and 2 plus 1, 3. So the available will now increase to 7, 4, 3. Now let's go and execute P4. So if P4 goes for execution, this available 002 will come to the, this allocated 002 will come to the available. So the available increases to 7, 4 and 5. So P1, P3 and P4 is done. Now let's go to P0. If we go for P0, P0 needs 7, 4 and 3. We have 7, 4 and 5. So if we give these resources, so once P0 executes, the alloc will come to available. So available becomes 7, 5 and 5. Now what is left out is P2. P2 needs 600 and we have 755. So once yeah, once P2 is also done, the alloc will come to available. So 7 plus 3, 10, 5 plus 0, 5, and 5 plus 2, 7. So this becomes this maximum, whatever was there, will come back to the system when all the processes executes. So this is a safe sequence. Okay. So actually, options were given, so you could choose from one of the option. There are other save sequence also because first itself we could have gone with P1 and P3. Similarly, in the second iteration, we could choose P3 or P4. So we just choose P1, P3, P4 in that order. Instead, we could have gone with P4, P2 also. But then from the choice, you have to choose. You have to find all the possible sequences which will be safe for deadlock free, and then from the given choice, you can choose one. Okay. Is this clear?
Yes, ma'am.
Okay. Right. So that was with respect to the source. Now, the next topic that was discussed in the previous lecture was threads. So, I'll quickly walk through it and then we can go to previous year's questions. So, what is a thread? So we have studied about process, right? We have studied about processes and we have studied that a process will have a code segment, data segment, it has registers, it have the stack, it have its page tables, heap, stack, all these things. And we have seen that operating system creates processes using the fork system call. Each process will have a process ID, all those things we have learned, right? Now, threads are nothing but we generally call threads as lightweight process. Okay. So we will have a process, okay, which is like a parent. And from this main process, we will have multiple lightweight processes running, and we call this process as threads. So threads are not as isolated like processes. So if we have two processes, P1 and P2, this is completely isolated. P1 is completely isolated from P2. They don't share anything in common. So if they have to have a communication, we need the interprocess communication mechanism. Okay, that is how processes work. They don't have anything common. It's completely isolated. Whereas in thread, they have their data segment and the code common. So threads have their data and code common. Whereas stack registers and all are separate. Hmm? So, but data segment and code segment are shared across the threads. And threads have something called thread ID, like how processes have process ID. Threads have thread ID. Since they are not completely isolated, it's very easy to have interprocess communication between the threads. It's very easy via the data segment, we can have the interprocess communication done. Sorry, inter-thread communication done. So it's more lightweight and the context switching across processes requires the complete context to be saved and restored. Whereas with threads, since these threads share the same data and code segment, the amount of switching that has to be done is minimal. And these threads are more lightweight and is more efficient with respect to context switching. Okay. We normally, why do we need these threads? That is, for example, one of the most common use case of threads is to parallelize the computation. Okay. For example, in the lecture video, sir have taken an example of adding the sum of like some billion numbers or so. If we assume we want to add the number 1 to 1000, I can have a for loop I equal to 1, I less than or equal to 1000, I plus plus, and sum equal to sum plus I. So this will loop from all the way from 1 to 1000 and we will sum it up. But instead of that, if this might, since 1000 is a small number, this will happen quickly. But if we take a very large n, like a billion or so, this looping will take time and this execution will take time. Instead, if we can parallelize this task, like we can split it to I equal to 1 to 250, then 251 to 500, 501 to 750, and 751 to 1000. We can have thread 1, thread 2, thread 3, and thread 4 process this one. And so it will have a sum 1, sum 2, sum 3, and sum 4. And once each of the threads compute the sum 1, sum 2, sum 3, sum 4, finally in the process the final sum can be computed as S1 plus S2 plus S3 plus S4. So this actually brings down the time required to compute the sum by almost 4. So for parallelizing the execution, we normally use threads. Okay. Now let's go back to previous year questions. Yeah. Stay true. Yeah. That's a program to is this true or false? Read through this. If my handwriting is not legible, I will read it. State true or false. A program to compute sum of first 10,000 numbers can be divided into 4 subparts and executed on 4 CPUs using either fork or threads. The reason why we prefer threads is because large portions of the data barcode between the 4 subparts are very similar and need not be duplicated. Is it true or false?
Ma'am, false.
This is actually true, right? Why is thread preferred? Because there are a lot of the context switching is very efficient with respect to threads. So that's the reason threads are preferred. And the reason why context switching is efficient is because that the data and code is shared across the threads. That's the reason context switching is efficient. So this is true. Okay.
Yes, ma'am.
Hmm. Yeah. Which of the following is false about user threads? I think I will. Okay. User threads can switch fast. One second. Okay. Give me a minute. Okay. Internal kernel. Yeah. The user threads are lightweight since they do not require system calls. Kernel is not aware of none of this.
Ma'am, none of these.
Yeah, correct. So user threads are in the user space only those user threads are executing. So kernel is not aware of them, and because kernel is not aware of them, kernel is not involved. There are no system calls, so they are fast also, and they are lightweight also. Okay, so none of this is the right answer. Next question, I will copy paste in the chat. Okay, taking time. Which of the following is not valid for deadlock prevention scheme? Which of the following is not valid for deadlock prevention scheme? Uh, Release all resource before requesting a new resource. So that is about hold and wait condition. Number all resources uniquely and never request a lower numbered resource than the last one requested. That is with respect to circular wait. Never request a resource after releasing any request. Then request and allocate all required resource before execution. So that also relate to hold and wait. So option 3 is not valid for prevention scheme. The answer is option 3. Never request a resource after releasing any resource. Next one is uh, hmm. An OS implements a policy that requires a process to release all resources before making a request for another resource. Which of the following is true based on the above statement? So this condition, what they're saying is that before asking release, if the process is already having some resource and it's again requesting, then the process has to release all the request before making another request. Okay, so this is with respect to the hold and wait condition. So if this happens, right, so we know that if this is done, hold and wait condition will not hold. If that condition is not holding, then one of the necessary hold and wait is one of the necessary condition for deadlock. So if we stop that from happening, deadlock will not happen. But this can cause that process to keep on waiting, because if it have large number of resources to be given, there is a possibility that the process might have to undergo starvation. So starvation can occur, but deadlock cannot occur is the right answer. Right answer is 2. Now stay true or false. True or false, sorry. Consider a situation when a dining philosopher's problem. Okay, this probably we can write. Oh, what is the answer here? Hmm. So for the dining philosopher's problem, We had 5 philosopher and 5 forks, so we have deadlock. Now, how many more fork was needed to break it?
Ma'am, 5.
5 more. 5 more is the ideal case. How many more was needed to just to avoid or prevent the deadlock? So one of the condition is the circular weight. If we can break the circular weight condition, deadlock will not occur. So how can we make sure that circular weight doesn't happen in the dining philosopher's case? So we had this, right? P1, P2, P3, P4 and P5. And we had F1, F, F2, F3, F4, F5. This, correct. So this is the circular weight condition. Now for us to stop the circular weight, if we just place one more fork here, sorry, will this solve the problem? So see, these people are sitting like this. P1, P2, P3, P4 and P5. Okay. So we had 1, 2, 3, 4, 5. Now assume that we had one more here. Will deadlock happen now?
No,
So
ma'am.
assume deadlock will not happen, right? So one more fork would break the circular weight condition. So deadlock will not occur. The answer is B. Okay. Hmm.
Okay, ma'am.
Okay. Another question. True or false? Hmm. Deadlock detection possible. Possibility. Hmm.
Ma'am, option A.
True, true, false. Yeah. Okay. Okay. So, mm, last question. I'll copy paste it in the chat. So, in a non-multi-programming operating system, a deadlock could occur. A deadlock could occur when two processes share the same resource. Can never happen when two processes run at the same time, waiting for resources held by each other, and an interrupt occurs. So, it's a not multi-programming OS. So, a deadlock can never happen. Okay. So, we are. Yeah, so we are yeah, pretty much done. So yeah.
And what is the answer in a non-multi-programming operating system?
It cannot happen. Can never happen because there is non-multi-programming OS, right? So one by one only executions happen. So can never happen.
Okay, ma'am.
Yeah. So yeah, that's all from my side. I'm done for today. So if there are any questions or if there are no more questions, then we can close the session. Thank you all for
Ma'am,
joining. Yeah.
ma'am, what should we do for the exam, ma'am? Like, what should we study? That is the question.
That actually I don't have much of an idea. Um,
Like any question, exam pattern, or any paper that will
no,
be going
I'm
to
not
see.
aware at all. I'm not aware because we take only this previous year question session. So we don't get involved in the exam part nor have no idea of how it was in the previous year also, how the questions were and not. So I actually honestly have no idea how the exams are put up.
Will it be an essay type or like a OMR type, ma'am?
Oh, OMR, I don't think it, but I have no idea to be frank. But will that be OMR? Do you have any information on the site?
No,
Will
ma'am.
it
Like
be?
in the mail, it came like it can be either
Uh,
essay writing
uh,
or
or
even multiple
OMR?
choices and multiple answers like that one.
So multiple choices could be like how the assignment questions are being given, right? So
Yes, ma'am.
from that, so my MCQ will be in those lines only. If it is essay, if it is like 5 mark of 10 mark descriptive answers are there, then probably like today we understood the concept of deadlock, right? We learned about the necessary and sufficient condition needed for it. The deadlock avoidance algorithm is Banker's algorithm. And so you can, I mean, that was touched upon. Then the other, the dining philosopher's problem, the synchronization solution for dining philosopher's problem. So in those ways, the 5 mark or 10 mark questions might come. I have no idea. This is just a guess. So if descriptive questions are there, then it could be from mostly from the theoretical side, and also like in the assignments, problems are also put up right in the assignment questions. So in
Yes,
those
ma'am.
lines also you can prepare. These all I'm just telling from nowhere, actually speaking. I have not seen previous year questions or have not have no, I don't have a, we actually take only this problem solving session. So we get to know the previous year's assignment questions only. We don't have any exposure to how the previous year's exam was or how the questions was. So yeah, this whatever I
Any
told is.
lecture,
Hmm?
like any lecture is related to the IIT course, so I can contact them
Hmm.
and ask about these things.
Whatever the like even in NPTEL itself, there are without even registering also you can go through all the lecture videos like operating system. There is another course. I think it's also available in NPTEL itself, which is a more elaborated three months course. So if you can go through them. Another thing is highly suggested is like there is a textbook on operating system from Silberschatz and Galvin, the Dragon book.
Silver shats.
Silber. Let me check the spelling. Give me a moment. Galvin and Silberschatz. I think its a copy should be available. Download them.
Okay. Okay, ma'am. Thank you.
Yeah, it is Silver Shats Galvin. So SILBERSCHATZ operating system concepts.
Okay.
And so
Thank
that
you.
is one standard book that is followed across, and it's very easy to follow textbook.
Okay. Thank you, ma'am.
Oh, yeah, sure. Sure. Any other queries? If not, I'll close the session. Thank you.
Thank you, ma'am.
Thank you. Bye.